Hello, everyone. So it's been unfortunate that we haven't been able to meet in stats for what will be now 2 weeks. But I'm putting this lecture together for chapter 2, which is frequency distributions. And then I will put another lecture together for chapter 3, which is, off the top of my head, I think it's central tendency. So we had started chapter 2, frequency distribution, the week before I had left for a week, before we didn't have our in-class session. So I'm going to kind of start over that again, go through it rather quickly because we did discuss it in class, but just so that we can be on the same page, as it was like several days since we last reviewed that. So let me go ahead and get that started. Don't mind the crazy inception here. Okay, so chapter 2, frequency distributions. So what we had talked about in class were these first two. So what is a frequency distribution? And this is in the category of descriptive statistics, and we talked about percentiles. And then when we group them together to kind of make classes, ranges for categories. But like I said, I'm going to go over that. I'll go over it kind of quickly. And then we need to make sure that we finish up with graphs and these fancy stem and leaf displays, which you may have heard of before, but we'll go over it. Okay, so what is a frequency distribution? Like I said, it's in the realm of descriptive statistics. It's going to be a way that we can simplify our data, simplify it and organize it so that when we look at it, we already grasp what is happening with the data before we analyze it, before we do any kind of statistics with it. Inferential statistics, I should say. So, and sorry if I'm going to be coughing on and off. I'm going to try really hard not to. So the primary job of descriptive statistics: simplify the organization and presentation of the data. Simplify it, make it concise, make it so that on a glance you can see what's happening. And frequency distribution tables and graphs do a really good job at that. Yeah, so one way to do this is through the frequency distribution. Formally, according to your book, a frequency distribution is an organized tabulation of the number of individuals located in each category of whatever it is that you're measuring, right? So if we have psych majors, our frequency is going to be how many people are psych majors. So in our case, I think it's 16 out of 17 of the students in this class, whereas the other major would be frequency of 1. So this is how you would put the amount of individuals in each class or category. So just a few examples of what that might look like if you either do it in a table or in a graph. So, who likes to drink Coke, Diet Coke, all these different sodas, your frequency or the amount of people in that. And we're usually, especially with a table, we're almost always going to have this total at the end. Where'd my mouse go? And of course, I always find a graph a whole lot easier to be able to read quickly. But here we have an additional component of a second variable with 2 levels to it, so kids and adults. We can see that kids really favor Coke. Maybe it's because it's their first caffeine that they get, who knows. Whereas then adults are going to favor Diet Coke because they're trying to watch their weight, right? So there's already things just looking at this that you can kind of deduce, especially if you know the population that you're talking about. We've talked about SAT scores and NCAT scores. I'm going to use those a lot because for one, it's something that we can easily relate to, and because they're taking from a rather large population, students of the United States, you have these really nice distributions that are nice and smooth. So for example, this one would be a normal distribution, and we'll keep talking about what is a normal distribution, but there's a lot of qualities to a normal distribution that we'll be going into detail. But basically, your super nice Gaussian curve, bell curve, inverted U curve, whatever you want to call it. So there are 2 primary elements, no matter if you're talking about a table or a graph. But like I said, most of the time I'm going to be preferencing graphs. But regardless, the first element is that you have different categories. So your categories are based on that original measurement scale. Right, so down here, your SAT scores would be the actual score that you get, right? You're measuring that from the people who are taking the SAT or the MCAT. And these are your categories. And we'll talk about this in a little bit in the slides, but sometimes we might also want to group categories or group scores together to make categories, right? Average score, above average score, super excellent score. And then we have another element that displays our frequency, or the number of people who are actually getting that particular score, right? So in a table, of course, frequency is going to be its own column here. Sorry. Frequency is going to be its own column. You can very quickly see how many people are in each. Here, your frequency is almost always going to be the y-axis, very commonly. Especially when we talk about scientific journal articles, frequency is almost going to be on the y-axis. But I'll show you some example where it's not, where especially in like popular magazines or websites, it's actually going to flip it. But regardless, you need these two elements, whether it's a table or a graph. You need the categories and you need the frequency, or the number of people in each. Yeah. So if it's in a table, they're going to be columns. If it's elements in a graph, it's going to be your axes, your x and your y axis. Okay. We had talked, the end of chapter 1, we had talked about sigma x, and we did a few calculations and you did a few homeworks with that. So now we can implement that with our frequency distribution table, where we want to sum up all of the elements, all of the scores that we have. So we have here the different scores that you can have, 1 through 5 happens to be sorted here, and then this is your frequency, right? So one person got a 5, one person got a 1, and everybody else kind of got in between, which is pretty normal for a normal distribution, right? So if you wanted to sum up all of these scores based on their frequency, you have 1 5, you have 2 4s here, so +4, +4, you have 3 3s, so 3 + 3 + 3, etc., right? And if you count those together, you get 29. What you can also do, much more practical, is you go ahead and make a new column where you multiply these together. So you go ahead and multiply your score by the frequency, right? 5 times 1, 4 times 2, 3 times 3. You go ahead and put that together, and then you can sum these guys up, and that will be the same as if you had summed it up going this way. In fact, it's a lot easier, right? So now we simply add these elements of our column together, 5 + 8 + 9 + 6 + 1, and then we get the same value, hopefully, if we didn't do anything wrong. I briefly introduced this in class. Like I said, I'm going to kind of skip over this, but I was using this as an example to talk about, because not everybody is a gamer, but it's actually a lot more common than you would expect. If you're looking at my backdrop, you might notice some Overwatch things in the background here. So Overwatch is definitely, it's been for the past several years, my go-to game. A few others here that me and my family play. But really, really quick, just general gamer statistics. The average gamer is 35 years old. So there are some old people playing. It's not just youngsters. People aged 18 to 34 make up about 40% of the gaming population. More of them are female than you think. There might, of course, be a breakdown in what types of games males versus females go for. A few additional, there's at least one gamer in 75% of American households. Yeah. And then I love this last one. In the US, 55% of parents play video games with their children, which is really great. So I was using this as an in-class exercise, if you remember, to figure out how many of us in class were gamers, and I believe it was actually 4 of us, myself included. So we actually had 2 girls, two females. I try to always say male and female, not girl or boy. 2 males and 2 females. So I underestimated how much we might actually be, although not out of 30. I think we're 17 in the class. But what you can do is you can calculate proportions and percentages, right? Of our class, our stats class, how many of us are gamers, or would we call ourselves gamers? Let me just go off on this because I don't feel like recalculating what it was. It's like 4 divided by 17. I can't do that off the top of my head. But for example, 2, or in our case 4, would be the frequency. How many individuals, what is the number of people in that particular category of gamers? If you wanted to figure out what is the actual proportion to the whole class, first you have to figure out your N, right? On the homework, I noticed you guys identified N, right? N times sigma of whatever. But make sure that if you have that information, put the value of N in there. Like, for example, in the homework, you usually had 5 values. So N will be 5 because that is your sample. So here, our sample in our classroom, I don't know why I thought we would have 30 people in this class. It's a bit of an overestimate. We're 17 people in this class, right? So if you want to calculate the proportion, you do the frequency of that category you're interested over the entire sample, and that gives you the proportion, right? So in our case, it would be, let me just do it really quick, 4 divided by 17. 4 divided by 17 is about 24. It's pretty good. So 0.24. This estimate is 0.067. Now, if we wanted to talk about percentages, we simply multiply that by 100. We multiply the proportion by 100, and then we get 6.7. Also, easy trick is we just move the decimal point 2 points over, right, if you're multiplying by 100. So with this estimate, 6.7% of the class was gamers. In our example, 24% of the class are gamers, actually. Okay. Percentile and percentile rank here just kind of comes down to also your terminology. So we've all experienced this before when we took the SAT. If any of you plan on taking the wow, brain fart. What is it for grad school? Something with a G. GRE, there you go. If you take the GRE, if you're going to take the MCAT, you're basically, the score that you get is often sent back along with a percentile or a percentile rank, right? So just to be clear, because I might have said that backwards just now, your percentile is your actual score, right? If you scored like 1200, 1300 on the SAT, that was your percentile, your percentile, your score. If you're trying to see, I'm so sorry. I tried to wait until I could record without coughing, but if you're trying to see how you rank between everybody else who took the score, or nationwide, depending on what the population is that it's taking it from, they calculate your percentile rank for you, right? So a score of 1220, for example, would equate to a percentile rank of 83%, right? It's the percentage. So if you're at the 83rd percentile rank, that means you did better than 83% of the people, like in your group or your population, depending on how they calculated it. And then 17% had a better score than you, right? So I think we're all familiar with this, but just make sure that you know the difference between percentile, your actual score, and percentile rank. Okay, cumulative frequency. This is also how you can basically determine a percentile rank for your data if you wanted to do that. So this is the same scores that we had before, 1 through 5. Different frequency distribution now. We have more people here in the middle. If we wanted to calculate what is someone's percentile rank if they get a score of 2 or if they get a score of 4, assuming these are somehow, actual rankings, as if like 5 is the better score than 1, you can do this where you calculate the cumulative frequency, and from that you can end up determining what the actual ranking is, or the cumulative percentage, which can translate to percentile rank. But basically, you add the previous one to it, right? So here, if you're at the bottom, your cumulative frequency, there's nothing to really add together. It's simply 2. For those who got the score 2, if you're looking at the cumulative frequencies, it's how many people had 2 and 1. right? So 4 people and 2 people, 4 plus 2. So 6 people had 2 or less. How many got a score of 3? 8 or less. 8 people had 3, 4 people had 2, and 2 people. So once you add those together, 14 people had the score of 3 or less, which equates then to 70% of your group, right? So anybody who would have above that score would be 30%, in the top 30%, so to speak. Does that make sense? As if I'm expecting people to nod back to me. And so how you can calculate that, your cumulative frequency that you put here in an additional column, just divide that by your population. Remember, big N is going to be for population, small n is going to be for your sample. So just make sure that you also know the the difference between those two. But it's the same with calculating a percentage. You know, whatever it is that you're interested in, divide that by your sample or your population, gives you a percentage you can work with. Okay, group frequency tables. I had said I would go through this quickly, and now I'm just going through at the same pace that I normally would. So group frequency distribution is when you want to make categories, right? You don't want for every single score know how many people got that, because maybe not everybody got on their SAT a 1221. Maybe some people, maybe we skipped that score and instead people got a 1222. So generally what we like to do is we like to make categories. And this is actually from my different apps will do this, especially when they gamify things for you. So this is from my Audible. Depending on how many hours of Audible you listen to, audiobooks, you know, you rank up. So I've listened enough now to where I'm at the scholar level, but I still have 157 hours more to go before I'm at the master level. Or for those who use, you know, running apps or anything else, where you kind of get like a little accolade or a reward, like, hey, you've done like 20 hours of workouts now, good job. But this is a way of actually, you know, grouping these frequency distributions together. I need to get a cough drop. So basically grouping like this, when you have a wide range of values, I put this in here, so data with a wide range of values, right? It's not going to be realistic to show the frequency for every single value, so instead you make ranges or you make categories. So categories for specific ranges, you group them together into intervals, and we call these class intervals, right? On these apps, you can call these class intervals. Usually we like to make it, and I'll show that in the next few, couple of slides. There's kind of a protocol or guideline on how you're supposed to group those together. You know, kind of even distribution of the class intervals. Sometimes it's not possible, and in an app like this, you don't have to follow that rule necessarily. If it's a table, if it's a group frequency table, then, you know, same thing, whether it's in a graph or a table. Okay, we did this in class, so I'm not going to go over this again. But I asked you for boba estimates, the bubbles and bubble tea. We had a few, like 2 people down here, and I think the majority were kind of in the 30 in these 2 categories, right? So one thing that some of these guidelines that I talked about is generally you're going to want to aim for about, it depends on your data, of course, but if you have enough data that you can nicely split it into 10 categories, 10 class intervals, that's a nice way to display what's happening with the data. For presentation purposes, sometimes we'll, you know, aim for a lower number so it's more visibly better for us to figure out what's going on. So that's actually, I didn't mean to do that, but that's what I did here. I have 5 class intervals. If it's in a scientific paper, often it'll be more than that, right? Because we're just trying to cram all the information in there. A second piece of guideline, other than how many class intervals we select, is the width of the interval, right? You want it to be equal. So all intervals have the same width, but you also want it to be a simple number, right? So here it's going to be basically every 10. Except for this last one here, right? So you might think, oh, this goes a little bit against these guidelines. And again, it depends on what the data is, you know. But generally, yeah, you might want to cut it off and not just have a greater than 50, because that goes against these guidelines here. Your bottom score also, usually a multiple of the width, which I did here, right, starting at 10. One thing to keep in mind, because these are kind of artificially created class intervals, these are not the same as real limits. When we talked about continuous measures and where you define, you know, the height of somebody, if they're 61 inches, 62 inches, 63 inches, the real limits to those are half weight to the next one, right? So it would be 60.5 to 61.5 is the real limit for a value that we call 61. This is not quite the same thing, because these are apparent limits versus the real limits in continuous measures. So just make sure that you keep those separate. Okay. Let me see. Okay. So now we can move on to frequency distribution graphs. So histograms. Coming back to the SAT scores. Histogram is basically, you have your x-axis, which is your measurement scale or your categories, right? It can be, if it's a grouped frequency distribution, it can be your categories or simply the measurements you're getting. And here you actually see that it is a grouped frequency, because 1000, 1050, 1100, 1150. So they didn't put every single score in here. It's every 50 or so that they split it apart. Your x-axis is your measurement. Your y-axis, this is your frequency. This is what I was mentioning earlier, right? Histograms are just very straightforward, beautiful way to display what is happening with the data. Your like I said, your y-axis, your frequencies, these are going to be your individuals if they are humans, but we don't always have humans. Maybe it's how many apples are in the store or whatever. Why is there always apples in a store? It's like, anyways, items, individuals, whatever it is. So in interval or ratio scores, remember we have 4 scales of measurement: nominal, ordinal, interval, and ratio. These last 2 that are numerical, these can be displayed with a histogram or a polygon. I'll show the polygon in a second. One thing to note here that I wasn't very precise on is a histogram is not going to have space in between these. This is actually, if there is a space in between, it's actually called a bar graph. So this wasn't the best graph to select to show you guys, but I'll reiterate that on the next slide, or on another slide. Is it this slide? Maybe. Okay, so if we have, for example, the frequency table here, right? Our scores, our x values, our frequency, we can pretty easily recreate even ourselves, either through this informal histogram where we just, each person is a block. We can add those together. This is not typically used in research papers. This is very handy just for illustrative purposes or educational purposes to kind of get the point across of how a histogram is made. But generally, we're going to have that x-axis down here, quiz scores, for example, and your frequency, right? So very clearly we can see even kind of like what the shape of the scores are. Down here is another example, and I should mention here, so actually I can never see my, oh yeah. When I'm doing this, I can't see if I have any notes in my PowerPoint. This top one here, these are discrete variables. So only whole numbers, 1, 2, 3, 4. These down here are is a continuous variable, continuous measurement. And so you can see these are children's height in inches, right? We were just saying that it's a continuous measure, has real limits. And in addition to the real limits, they made a category of a 2-inch class interval. So you can see how that kind of breaks down. These are presumably, let me see. I don't know what age this would be, but obviously This is different ages of children. But one thing you can see here, this sometimes happens, the x-axis down here is broken off, and that's because we're not displaying it from 0 up, because even a newborn has some inches on it, usually, like 19, 20 inches or something, right? So if we're to properly show that we're not starting from 0 and going up, because we're not going to have any values there, we can do this break symbol that says we're just starting at 30. But then same thing, you have your categories down here, your x-axis and your frequency. Okay. So polygons are really no different than a histogram. You're just removing that giant block or bar, histogram bar underneath it, and you're just left with the envelope or kind of the outline of the shape of that histogram. Sometimes this is easier to see depending on the data that we're talking about. You can see the shape better because you're not distracted with all the stuff that's filled in underneath. It's very common to use these polygon graphs in developmental psychology or behavioral analysis. So for example, they're trying to do some behavioral modification. Your your y-axis here is frequency of behavior. So for example, phase A is your baseline. Let's say this is, let's just say this is in a introduction of IV, in a hospice, and you have elderly that are fighting together, right? And you have a team of psychologists that come in and are trying to implement some type of behavioral modification program to help the old people to stop yelling at each other, right? So first you need a baseline. You observe them over 5 or 6 days, and you get a measurement of how frequent, for example, pro-social behavior is happening, right? So rather than yelling at each other, how often are they nice to each other? And down here, you see, oh, we're only recording a few instances of them being nice to each other. Then phase B is when you start introducing your treatment of some kind, right? So some type of behavior modification, trying to change their behavior, maybe like introduce like tokens or rewards or something. And you can measure every set of 5 days. How is that going? And you can see, oh, there's improvement happening, especially here at the end, right? So the frequency of the behavior, your pro-social behavior, increases. So what I'm trying to say is the polygon graph is a better way to show this so that you don't just have all of these bar graphs underneath it or histogram underneath. So it's just a preference. They're really no different how you put these together. It's just a nice way of showing the data, especially if you're trying to see how is it changing over time. Okay, bar graphs. So I was using it interchangeably, which is bad, but histograms and bar graphs are different, and you use them for different scales of measurement. So a histogram, what I've been showing you thus far, is for numerical data, so interval or ratio. If you're using nominal or ordinal data, so non-numerical, usually it's non-numerical, we use a bar graph for these. And in a bar graph, there's going to be spaces in between the bars. That's what I was mentioning, that my SAT one here was actually not a good demonstration of that because there was a space in between it. This one, however, histogram, no space in between. These are numerical data, right? Whether it's discrete or continuous. But when we're doing a bar graph, it's for nominal ordinal data. So this right here, this is pretty interesting. The world's most popular theme parks. If some of you are not from Florida, welcome to the land of theme parks. Obviously, Disney World, Disneyland, Disney World. I promise I'm from Florida. And Universal Studios. Universal Studios is like all the way down here. But Magic Kingdom, right, these are almost all going to be in Orlando. Magic Kingdom, over in California, we have 2. So Disneyland Park and Adventure Park. Tokyo actually is pretty much up there. Oh, and there's a Chinese one too. But otherwise, Disney's Animal Kingdom, Epcot, right? So when you look at this, these categories, first of all, and I know I can't talk to you right now because this is recorded, but what kind of data would this be? Would this be nominal or ordinal? Right? Magic Kingdom versus Universal Studios. Are these comparable? Can we actually compare? Is there some quantitative way in which we can compare the two? If there is, then it would be ordinal, right? But otherwise, I would say this would be nominal data because there's no real way to quantify the difference between Epcot and, I know, Tokyo Disney Sea, right? Although here it's being ranked by popularity. So if it's being ranked, then maybe you could speak towards it actually being ordinal. The other thing is, where is the x-axis for this? This is what I was mentioning earlier. Don't always think that the x-axis is on the bottom and that the y-axis is what like goes up. You have to know what it corresponds to. So the x-axis are your categories, the things that you're measuring, right? So your x-axis here is flipped. This is your x-axis because these are all the different places, the popular theme parks. And our frequency is going to be the y-axis. So our frequency is actually going sideways like this. This display here is very common in like news outlets, magazines, websites. Also because you have to write this out, right? You have to write out Magic Kingdom. Otherwise, it's hard to read if everything's on the bottom. Research articles almost always have the x-axis on the bottom. And then y-axis is the frequency. But don't be fooled by that. Also, it's a bar graph because there's spaces in between the bars. But yes, your frequency here in millions, right? These are going to be your frequencies, so that's going to be your y-axis. Population versus sample, right? So if you end up having an extremely large sample or an actual population, all of the individuals in that population that you're studying, we don't use absolute frequencies. We switch over to relative frequencies. So for example, here we're going to be switching to percentages. So if we did a survey of all pet owners, let's just say dog owners, and we asked them, how do you feel your dog, how do you feel about your dog? Is it, do you consider them a family member, a companion, or property? And you can see that the majority of Americans, about 60%, would say, oh, they're definitely part of the family. Maybe about 35% view them as a companion, and a very small percentage, fortunately, think of them as property, right? But these are not showing absolute values. It's not saying 20 million people think that they're family, 15 million think that it's a companion. When you have such large numbers, the entire population or a very, very large sample, you switch over into having relative frequencies, specifically percentages, right? And another thing is that you end up having very smooth curves because all of that data is basically where you maybe had spaces in between, like a lack of scores. Because you have such a large number, like thousands or millions of people, it smooths everything out. And so your envelope, remember like the polygon, your envelope ends up being nice and smooth. And depending on what the data is, most of the time we end up falling into the normal curve, right? And we're going to keep encountering this guy, but this is a nice normal curve. Okay. Yeah. Normal curve, normal distribution, also very symmetrical. So I think that's the next thing that we're going to talk about is the shape of the curve. When we talk about central tendency, like the mean, the average, the mode, the median, that will be the next chapter. And variability, what influences the shape? Like, is it a skinny shape? Is it a fat shape? That's going to be variability, and that'll be chapter 4. That won't be on exam 1. We'll cover that after our exam. But first of all, the shape. So we can have symmetrical distributions, right? A normal distribution is going to be symmetrical. We can also not just have one hump, but two humps, right? One is like a camel and the other is a... Oh my god, I forgot the name. Anyways, we can have two humps here. And you may remember this from like a prior, stats class or introduction to science type class. We call this a bimodal distribution. And we'll revisit this again in the central tendency because mode, there's a particular quantitative measure that corresponds to the mode. But this would be a nice symmetrical normal distribution. This would be a symmetrical bimodal distribution. Two large values that are occurring. The other shape that we can have are skewed distributions, right? And depending on the data that we're talking about, sometimes this is the more common one. We can either be positively or negatively skewed. Now, in order to remember which one is which, because it's easy to kind of like be like, it's like skewed going in one direction. How would you know? This is what I do. Identify where the tail is tapering off. So for example, for this one, the positive number is up here. The tail is tapering off into the positive side. So it's a positive skew. On this one, the tail is going into more negative numbers. So it has a negative skew. So do whatever you need to do. Use something else to remember the difference between the positive and negative skew. Where is the tail going? Not where all of the data is, but where is the tail going, right? Tail is going off into the positive. Most of the data is up here, but the tail is going off into the negative. Okay. Yeah, so some illustrations of shapes. This one's funny. I love doing graphs like this, where you basically, down here's your x-axis, sleep time. So 10 o'clock, 11 o'clock, 12, 1, 2, 3. When people go to sleep, during the weekday or during the weekend. So during the weekday, the majority, if we're talking about, the biggest hump, is, 12 a.m., somewhere between 11 and 1, with a majority, the average, seeming to be centered around here, right? But then on the weekends, it shifts to the biggest hump here being 2 a.m. So think what kind of skewness this would be, right? Because this one looks pretty normal. There's some people who go to bed really, really late here. But once we go to the weekend, it shifts and our distribution gets skewed. So I'll let you think about which one this is, but what type of skewed distribution would this be, positive or negative? We can also have different shapes and not be skewed, right? This is height of men and women. We know that generally men, on average, right, it's a distribution, are going to be taller than women. Of course, you can see there's a proportion here of women that are taller, right? And there's a proportion of men here that are shorter. But generally, when we say that men are on average taller than women, we're talking about how the distributions are aligned. And one difference that you can see, both are normally distributed because we're talking about a very large population, all the men and women of the United States, for example. But the shape is different. And we'll talk about this in chapter 4, the variability. Specifically, it's called the kurtosis. So basically, how pointy versus how flat the curve is. The women's curve is like, you don't have as many values. It's more pointy versus the men, it flattens out. So you have more variability, more actual options of height for men, right? So that's another way that we can talk about the shape of a distribution. This one I think I briefly showed in class, but here we have another example of what first looks like a normal distribution, but then we have this little category here of how many hours do law students spend reading for class. Most of them will say 16 to 20 hours, and by most I just mean based on the normal distribution here. But you have a 7% here that spend more than 35 hours. And on a normal distribution, just like up here, we're going to start tapering off, and that's not the case here. So we have a case here of a skewed distribution. Again, think of whether or not this would be a positive or a negatively skewed distribution. And another example, first, of a skewed distribution. Again, think whether or not this is positive or negative. This is going to be a little bit more difficult because the graph is flipped, right? And then that's the other part. Can you identify what the x-axis is and what the y-axis? You have to know what the x corresponds to. So x is going to be your categories, your measurement, and y is going to be your frequency, right? So practice that on your own. See if you can identify the skewness, positive or negative skewness. This one was switching into the pandemic. A lot more people started spending time watching television or sleeping. Okay. And then we have one more section for chapter 2. The last part, this is very straightforward, but it's just another way to show our frequency distributions. These are stem and leaf displays. Okay, so the number 85, what you're going to do for a stem and leaf display is you're going to split it. Basically the, what do you call it? The, my brain is like fuzzed out. I can't think of the word, but I'll just walk you through it. The stem is going to be the, like the 10 digits. Why can't I think of what the word is? 80, basically, right? If we're in the 80s, that's going to be the stem. The 5 is going to be the leaf. So for example, if we have a whole bunch of different 80 values, 81, 85, 86, 89, these seem like birth years for millennials like myself. Your stem is going to be the same because they're all 80s, but you're going to have 4 different leaves because you have 81, 85, 86, and 89. And typically we also sort them when we put it in the leaves are sorted from smallest to largest. If we have not just 80s, but we also have teens and 20s and 140. What does this mean for the stem? We're going to have 4 different stems now. And these are also sorted usually. So we're going to have 2 different teens, so 15 and 13. I guess I didn't sort it here. Look at me. 15, 13. We're going to have 2 20s, so 29 and 22. 140 values, so 46, and 2 80 values, 81, 85. So this is very similar to the grouped frequency distribution where we make class intervals, but this is reliant on the word that I can't think of, not the decimal point. I guess it would be the decimal point, but basically 10s, 20s, 30s, and 40s, right? So the stems are the categories based on whether we're talking about 20s or 40s. I think what I meant to do here was resort it. Maybe it isn't a hard and fast rule that it has to be sorted. Because generally, if you're trying to put this together, you're trying to be quick. So you're just going and reading through and writing it in. I think best practice would be that you sort them. But when you're putting it together, that's fine. All right, one example. For the score shown in the stem and leaf display over here. So it looks like we have 90s, 80s, 70s, 60s, and 50s. What is the lowest score in the distribution? Right, so it looks like we have 390 values, 380 values. So I'm going to leave this to you to think about. You're trying to find the lowest score in the distribution, right? So first find your stem and then find your leaf that denotes the smallest number. Okay, so that was chapter 2. Let me see. I wonder how long that recording went. But hopefully that helps. I'm really sorry we could not do this in person. I'm sorry that things are not quite the way that I want them to go. But despite a cough, I think Monday, or rather Tuesday, we'll be able to meet again in person. I hope everyone saw the announcement that I moved the exam from Tuesday to Thursday so that we can meet in person, go over what to expect, do any kind of review of these chapters. I will also be recording I will be recording chapter 3 and uploading that as well. But until then, I will see you in the next recording, and then I will hopefully see you in class on Tuesday. All right, bye guys.